Hello, I would like to welcome you to this presentation for the ISC 2020 conference. My name is Giorgis Georgakoudis and I work at the Lawrence Livermore National Laboratory. I will be presenting you the paper Reinit++, evaluating the performance of global restart recovery methods for MPI fault tolerance. I would like to introduce my other co-authors, Luanzheng from University of California at Merced and Ignacio Laguna from Lawrence Livermore National Laboratory as well. Discussing why MPI fault tolerance is important, we see that our HPC systems scale to include more computing nodes, larger interconnects, and more storage. And although they become more powerful by including more hardware components, they also become more prone to failures. There are two kinds of failures that can happen. One is soft errors, which are transient failures like bit flips happening in memory, not being correctable by ECC, and hard errors, when something is malfunctioning and stops working. These failures are especially relevant for MPI scale-out execution, and our research addresses this problem. Global restart is a widely used method for recovery from failures. This particular recovery method fits very well HPC applications that follow the bulk synchronous processing paradigm, which is the most widely one used. So MPI processes execute, and during their computation, they also store checkpoints of application state. When there is a failure, the system recovers, and then the same number of MPI processes resume execution by loading a checkpoint to continue computation. Global restart recovery has three attributes. It is backwards recovery, meaning that computation moves back in time to a consistent checkpoint to resume. It is non-shrinking, because the same number of MPI processes after a failure are going to resume execution as the number of MPI processes before the failure. And it is global, because all MPI processes, failed and non-failed ones, participate in recovery. There are three methods to do global restart recovery. The first one is the traditional checkpoint restart. And for checkpoint restart, when a failure happens, the application execution stops, and then the application needs to be relaunched. And although this is an easy way to do global restart recovery, it also comes with high cost of redeployment, because the MPI processes need to start again on all the nodes in the system, and any application-specific initialization needs to happen again, even if there is a single process failure and all the other processes have survived. There are two approaches that allow to improve on that by saving the deployment overhead. One is by using the user-level fault mitigation, which is an MPI extension that gives an API to shrink and merge communicators. This interface is very powerful, but it is hard to use by application developers because it requires them to have intricate understanding of the semantics of those operations. Reinit is another interface to do global restart recovery with MPI. It is tuned to do only global restart, but it is very easy to use. To talk more about the Reinit MPI interface, it has a single MPI function call, MPI Reinit, which mirrors the argument of MPI init. So it has an argc and an argv parameter, and extra, it has another argument, which is a function pointer to a resilient function. This resilient function is going to be called whenever there is a process failure or a node failure in the system. The resilient function takes as arguments the argc and argv parameters, and also takes an extra argument, which is the MPI state of the calling process. This state can be new if the process is executing as a new process that hasn't experienced any failure so far. It can be reinitiated if this is a survivor process after a failure that has been reinitialized calling again the resilient function. Or it can be respawned if this process have been started to replace a previously failed process. Calling the resilient function has similar semantics for MPI state as MPI init. So the number of ranks when calling this function is the same as the number of ranks before the failure. And the valid communicators are the MPI com world communicator and also the trivial communicators self and null. We saw examples on how to write a Reinit-enabled application for global restart recovery, and also how to contrast that with an equivalent implementation using ULFM. So looking on the code on the left for Reinit, we start with the main function. The programmer would call MPI init to initialize the MPI runtime, and then it would go forward with an initialization of the application. Then the call to MPI reinit provides the entry point resilient function, which encapsulates the execution of the computation. Specifically, the resilient function will load a checkpoint, if there is one, and then go through the main computational loop, going into cycles of computing and storing checkpoints. Last in main is the call to MPI finalize that tears down MPI execution. Comparing this with ULFM, we start again with the main function. Again, there is a call to MPI init to initialize the runtime and an initialization of the application structures. Then the programmer needs to put a jump point for rolling back execution in case of a failure. And then the programmer needs to set an error handler on the communicator to trigger when there is a failure. Following is the call to the resilient function that performs the main computation loop. So when a failure happens, the error handler is going to be triggered, and the programmer needs to shrink the communicator, spawn a new process, and then merge this to create a unified communicator, and lastly jump to the rollback point. Clearly, the implementation with Reinit is less involved and requires less understanding of internals than the implementation with ULFM. So we present Reinit++, which is our implementation of the Reinit API that supports automated recovery through the MPI runtime. The Reinit++ MPI runtime detects failures for both processes and node failures, and it automates global restart by creating new processes whenever there is a process failure or node failure in the system, and by reinitializing survivor processes. Looking closer on the design and implementation of Reinit++, it assumes hierarchical MPI deployment, which is common in modern MPI runtimes. For this deployment, the root process spawns a number of node daemons on each of the nodes that are participating in the application. The root process communicates to these node daemons through some reliable transport. Those node daemons then spawn the children MPI processes that are going to be performing the application computation. Looking more closely at how Reinit++ detects failures, and in particular process failures, the node daemon detects that a child MPI process has failed by catching the SIGCHILD signal. When it detects that, it forwards this notification to the root through messaging. The root will initiate recovery, as we will see later. Detecting node failures is different because the root process directly detects that a daemon has failed by sensing that the communication channel that it had with this daemon has failed. So it assumes that all MPI processes on that node are lost and that effectively this is a failed node. Looking at recovery from process failures, what happens is that the root process, when it detects a process failure, it sends a reinit command to all the node daemons in the system, and it adds as a payload to that command the identifier of the failed process. When node daemons receive this command, they roll back survivor processes to execute again the resilient function by sending a signal. Especially for the node daemon that was the parent of the failed process, when it receives this command, it also spawns a new process to replace the failed one. Recovering from node failures is similar The difference is that the deployment of Reinit++ assumes that shadow nodes are provisioned that are able to replace any node failures. In the case that the root process detects a node failure, it broadcasts again a reinit command that includes as payload the identifiers of all the MPI processes that have been lost due to the node failure. When node daemons on surviving nodes receive this command, they roll back their local MPI processes. When the node daemon on the shadow node receives this command, it spawns all the MPI processes that have been failed because of the node failure. The last step is application level recovery. And for that, Reinit++ assumes that the application will load the checkpoint to resume execution, and also that it will recreate any needed MPI state for computation besides the MPI COM world that is provided by the Reinit++ MPI runtime. We have implemented Reinit++ in OpenMPI and provide our implementation publicly in GitHub. Specifically, we extend OpenMPI version 4, and to give more details, OpenMPI has a software architecture with 3 distinct components. One is the OpenMPI MPI layer, UMPI, which implements the MPI specification. Reinit++ extends that to add the implementation of MPI Reinit. Then there is the OpenMPI runtime environment, ORTI, which implements the runtime functions that are necessary to support MPI execution. Reinit++ extends that to implement MPI recovery and the root daemon communication. Lastly, there is the Open Portability Access Layer, OPAL, that abstracts operating system and hardware interfaces. Reinit++ uses those interfaces for sending and handling signals, and also to spawn processes. Our evaluation compares checkpoint restart, ULFM, and Reinit++ using 3 HPC proxy applications, CoMD, HPCCG, and LULES. We experiment by scaling the number of ranks of deployment to test how well different recovery methods scale. We do fault injection to emulate failures, and specifically, we either do a single process failure during the whole of execution or a single node failure. We measure execution time by doing 10 independent runs, and we show 95% confidence level intervals in our plots. For checkpointing, we have 2 strategies. One is file checkpoints, which means that checkpoints are stored and loaded in persistent storage, and in particular in the parallel file system accessible by all nodes. And we also implement in-memory checkpoints, where checkpoints are stored and loaded in the process memory and also to a body process memory region. Depending on the recovery mode and the failure, we use different checkpoint, which is optimal in each particular case. When there is either a process or a node failure, checkpoint restart needs to use file checkpoints because it tears down MPI execution, so all the memory in processes is lost. For process failures and ULFM and Reinit, because they do online recovery and most MPI processes are alive, we do memory checkpoints. The survivor processes load their checkpoints from their own memory, and the failed processes load their checkpoint from a body memory region. Now, when there is a node failure, there are multiple MPI processes failed, and in that case, memory checkpoint with the body system cannot help. So even for ULFM and Reinit, we do file checkpoints. We compare overall execution time between different recovery methods, and we show this plot on the right for the CoMD application, and note that results are similar for other applications as well. On the x-axis, we show the number of ranks as they scale, and on the y-axis, we show bars for overall execution time. We split the overall execution time into 3 different components: the time needed to write checkpoints, the time needed for pure application computation time, and the time needed for MPI recovery. We don't show time for reading checkpoints because this happens one-off and it's a very small percentage of execution. What we see from the plot is that Reinit++ is significantly faster than checkpoint restart and ULFM, and that it scales very well. Also, checkpoint restart and ULFM show different bottlenecks. So specifically for checkpoint restart, file checkpointing becomes a bottleneck as the number of ranks increases. For ULFM, it does in-memory checkpoints like Reinit++. So its performance is lost because ULFM inflates application execution time for pure computation due to its operation. We look closer into application time by showing a plot that shows just how this time scales by the number of ranks. What we see is that checkpoint restart and Reinit++ have no effect on the application execution time as the number of ranks increases. But on the other hand, ULFM inflates greatly application execution time, the more the number of ranks increases as well. We are not sure whether this is an implementation issue or whether this is systemic in the way ULFM works. But we pin down the differences, and those are that ULFM needs heartbeats to do failure detection, and also it needs to use different set of collective operations that are made resilient for failure detection. Those two things add overhead and make the execution time of the application increase. Also, we compare MPI recovery only time for all recovery methods to factor out application execution time and checkpointing time. On the plot on the left, we show MPI recovery time for a process failure, and on the plot on the right, we show MPI recovery time for a node failure. Starting with process failures on the left, what we see is that ULFM and Reinit++ are recovering much faster than checkpoint restart. This is understandable given they save the redeployment overhead of checkpoint restart. Looking at node failures, we do not show ULFM because we were unable to collect results from it, but we contrast checkpoint restart and Reinit++. And what we see is that Reinit++ is recovering much faster than checkpoint restart for node failures, and that it also scales very well as the number of ranks increases. So concluding, we have presented Reinit++, which provides global restart recovery by extending the MPI runtime. It is easy to use and scales very well, and it also has much faster recovery than checkpoint restart and ULFM. As future work, we are drafting a specification for MPI in the context of the fault tolerance working group. We are looking to integrate Reinit++ with multi-level checkpointing methods like FTI and SCR, and we are considering to support more recovery options besides global restart, like stringing and forward recovery. Thank you very much for watching this presentation, and feel free to contact me by email for any questions.